Algorithm efficiency optimization strategies. In today's data-driven world, the performance of algorithms has become a critical factor in determining the success of software systems. As developers tackle increasingly complex problems, understanding how to optimize algorithmic efficiency is essential. This article explores advanced strategies that can significantly enhance the speed and resource utilization of your code. The journey toward efficient algorithms begins with recognizing the hidden costs embedded within seemingly simple operations. From memory allocation to cache misses, every decision affects runtime performance. Let us delve deeper into these optimization techniques that transform average implementations into high-performance solutions. The Big O notation, a fundamental concept. Big O notation provides a mathematical framework for analyzing an algorithm's time complexity. It abstracts away constants and lower-order terms, focusing solely on growth rates as input sizes increase. Understanding this concept enables developers to make informed decisions during implementation. This notation helps identify which parts of an algorithm may cause performance issues at scale. By examining worst-case scenarios rather than average cases, we gain crucial insights into potential bottlenecks. The key lies in comparing different approaches using standardized metrics. Common complexities include O(1), constant time operations regardless of input size. Log n, logarithmic growth typically seen in divide and conquer methods. N, linear time proportional to input size. N log n, common in sorting algorithms like merge sort. N superscript 2, quadratic time often found in nested loops. 2, exponential time associated with brute force solutions. Mastery of Big O analysis allows programmers to select optimal algorithms for their specific use cases. However, it is equally important to remember that real-world performance depends on various factors beyond theoretical limits. Time complexity analysis techniques. Analyzing time complexity requires careful examination of each operation within an algorithm. Developers must consider both sequential execution and recursive calls when calculating overall complexity. This process involves identifying dominant terms that dictate asymptotic behavior. For iterative algorithms, counting loop iterations proves essential. Nested loops contribute exponentially higher complexity compared to single loops. Recursion introduces additional layers requiring meticulous evaluation through recurrence relations. A practical approach involves considering best dash, average dash, and worst-case scenarios separately. While Big O focuses primarily on worst-case situations, other analyses provide a more complete picture of expected performance characteristics. Tools such as amortized analysis help understand average case performance across multiple operations. These techniques are particularly useful when dealing with dynamic data structures where individual operations might have varying efficiencies. Space complexity considerations. While time complexity receives significant attention, space complexity plays an equal role in determining algorithm efficiency. Efficient memory usage prevents excessive swapping between RAM and disk storage, maintaining system responsiveness under load. Developers must carefully balance trade-offs between time and space requirements. Sometimes sacrificing some processing speed for reduced memory consumption yields better overall results depending on hardware constraints. Considerations include memory allocation patterns affecting cache performance, data structure overhead impacting actual usable memory potential for garbage collection, pauses in managed environments, caching mechanisms that store intermediate results, recursion, stack depth. Limitations. Evaluating space complexity often reveals opportunities for improvement through optimized data representation. Choosing appropriate container types based on access patterns can dramatically reduce memory footprint without compromising functionality. Optimization through data structures. Selecting the right data structure can drastically impact algorithm efficiency. Hash tables enable constant time lookups while binary search trees offer logarithmic insertion/deletion times. Each choice comes with its own set of trade-offs. Understanding access patterns is vital for choosing suitable data structures. Random access benefits from arrays, whereas frequent insertions require linked lists. Spatial locality considerations influence cache performance as well. Certain applications benefit from specialized structures like tries for prefix matching or Bloom filters for probabilistic membership testing. These advanced constructs address niche but important use cases effectively. Profiling tools help identify bottlenecks related to data manipulation. By measuring actual performance gains from structural changes, developers can make data-driven decisions regarding optimizations. Loop unrolling and other code-level optimizations at the code level, simple transformations can yield significant improvements. Loop unrolling reduces iteration overhead by executing multiple steps per loop cycle. However, this technique increases code size, which may affect instruction caching. Caching frequently accessed values eliminates redundant computations. Temporal locality principles suggest storing recently used items near current execution context for faster retrieval. Proper register allocation also contributes substantially to performance enhancements. Best practices include leveraging compiler optimizations when available, minimizing conditional checks inside tight loops using bitwise operators instead of arithmetic equivalents where applicable, reusing variables rather than creating new ones unnecessarily. Pre-computing values before entering intensive computation phases. Modern compilers perform many automatic optimizations, but manual tuning remains effective in critical paths. Profilers help pinpoint areas where hand-coded optimizations produce measurable benefits. Parallel processing and concurrency models distributing workloads across multiple processors opens new avenues for improving algorithm efficiency. Parallelism becomes feasible when tasks exhibit independence, allowing simultaneous execution. Careful design ensures safe concurrent modifications without race conditions. Concurrency models vary from shared memory approaches with locks to message passing architectures. Selecting the right model depends on problem domain characteristics and available infrastructure capabilities. Types of parallelism include data parallelism, applying same operation to different data elements simultaneously. Task parallelism, executing independent tasks concurrently. Bit-level parallelism, exploiting wider word sizes in processor architecture. Instruction-level parallelism, overlapping instruction execution stages. Hybrid approaches combining multiple forms of parallelism. Effective synchronization mechanisms prevent deadlocks and ensure correct program state transitions. Load balancing distributes workload evenly among processing units, maximizing resource utilization. Cache-friendly algorithm design. Modern computer architectures rely heavily on hierarchical memory systems. Algorithms that respect cache line boundaries experience dramatic performance boosts due to reduced miss penalties. Spatial locality improves cache hit ratios through contiguous memory accesses. Temporal locality suggests reusing recently accessed data before evicting it from cache. Blocking techniques rearrange computations to maximize reuse within limited cache capacity. Memory alignment considerations also play a crucial role in minimizing access latencies. Strategies for improved cache utilization. Accessing data sequentially rather than randomly whenever possible. Aligning data structures along cache line boundaries using smaller data types when precision allows. Locality-aware partitioning of larger datasets. Prefetching data into cache before it's needed. Profile-guided optimization assists in identifying cache-related inefficiencies. Compiler hints can direct memory layout choices to align with hardware characteristics for maximal performance gains. Benchmarking methodologies for performance evaluation. Accurate benchmarking establishes baseline measurements against which optimizations can be evaluated. Controlled test environments minimize external influences, ensuring reliable comparison results between different implementations. Microbenchmarking isolates specific operations for precise measurement, while macrobenchmarks assess end-to-end performance metrics relevant to application goals. Both approaches complement each other, providing comprehensive insight into algorithm behaviors. Key aspects of good benchmarking include warm-up periods allowing JIT compilation and initialization, statistical analysis of multiple runs reducing variance effects, measuring both wall clock time and CPU cycles, tracking memory allocations alongside execution duration. Replicating production-like workloads for meaningful comparisons, automated testing frameworks support continuous performance monitoring, enabling early detection of regression issues. Comparative benchmarks highlight relative advantages/disadvantages of competing algorithm designs. Practical examples of efficiency improvements. Real-world scenarios illustrate tangible benefits from algorithmic optimizations. Sorting algorithms serve as excellent examples showing how changing strategy can lead to order-of-magnitude improvements in execution time. Replacing bubble sort with quicksort reduces complexity from O(n) superscript 2 to O(n) log n. Similarly, using radix sort over standard comparators produces linear time performance for numeric datasets. These shifts demonstrate why choosing appropriate algorithms matters critically. Other notable cases include switching from naive matrix multiplication to Strassen's algorithm achieving subcubic complexity, implementing fast Fourier transforms for signal processing applications utilizing graph traversal optimizations in social network analytics, applying tree-based solutions for auto-completion features, adopting Bloom filter implementations for duplicate checking scenarios. Performance profiling identifies specific pain points warranting targeted improvements. In many instances, even minor adjustments to existing algorithms deliver substantial gains without rewriting entire components. Trade-off analysis between time/space complexities. Efficient algorithms often involve balancing trade-offs between time and space requirements. Solutions that save time at the expense of increased memory consumption need careful consideration of platform-specific constraints. Choosing between O(n) space for O log n time versus O(1) space for O(n) time depends on available resources and performance priorities. Hardware advancements continually reshape what constitutes acceptable trade-offs. Fundamental questions arise during optimization. Is extra memory worth the time savings? What are the consequences of out-of-memory errors? How do different platforms handle memory management differently? Can we leverage hardware-specific features for acceleration? Are there alternative representations offering better efficiency profiles? Evaluating these questions systematically leads to more robust implementation choices. Sometimes hybrid approaches combining multiple strategies prove most effective in practice. Emerging trends in algorithm optimization. Advancements in computing technology continue reshaping optimization landscapes. Quantum computing promises revolutionary breakthroughs, although widespread adoption remains years away. Current trends already show exciting developments influencing traditional approaches. GPU computing leverages massive parallelism available in graphics cards for general-purpose tasks. Specialized hardware accelerators target particular domains like machine learning inference or cryptographic operations. Notable recent innovations include approximate computing relaxing strict accuracy requirements for performance gains, neuromorphic computing, mimicking brain architectures for novel processing paradigms, hardware-software co-design optimizing interactions between execution layers, probabilistic data structures simplifying certain computational problems, automatic differentiation, streamlining numerical computations in ML contexts. These emerging fields present fresh challenges and opportunities for algorithm designers seeking maximum efficiency. Staying updated with technological advances ensures continued relevance in solving complex computational problems efficiently. Conclusion: mastering algorithm efficiency demands a multifaceted approach combining theoretical knowledge with practical experimentation. By understanding core concepts like big O notation and implementing strategic optimizations, developers can create highly performant solutions tailored to specific needs. Continuous learning and adaptation remain crucial as technologies evolve rapidly. Employing proven methodologies alongside innovative approaches will position professionals at the forefront of modern algorithm design and optimization efforts.